we have a discussion. Anybody want to raise a question or raise some comments or ask somebody a question or suggest anything? Let's try to stay away from these 6 questions. But anything else? Anybody want to make a contribution to anything? Brian, you were here a lot. Do you want to ask somebody something? All right. Louis.
I have a question.
Good.
It's not for you, Jeff. I have a question for Louis and Eddie. Maybe for other people too, because, you know, it's starting to give me a headache. You know, is quantum theory really a generalization of Kolmogorov's theory or not? That's my question. And when I talk to Eddie alone, he says no. If I talk to Louis alone, he says yes. And so I want to know, what is the answer to this question?
Yeah, we have seen that, you know, the answers depend on exactly how you define Kolmogorov probabilities.
Yeah, right.
The way I define it, it is all-encompassing, and encompassing also the modifications Louis was talking about.
So Louis is defining,
In principle.
Louis is defining maybe a more restricted version. You're defining a more general version.
I'm just saying that if you allow for multiple sample spaces and
I find this very frustrating.
to be logical consistent, and then you are thinking in terms of confidence between them, then it is all encompassing. If you are talking about probability, the Kolmogorov probability theory as the theory of a single sample space, of course it's very
You can't
but it's not
take
a
aim.
So you can just define it in this way and, you know, say that something generalizes it. In some sense, you know, the as you know, as you yourself presented it in these very terms, that what quantum probability does, it allows you to construct not a joint distribution given known marginals, but rather a joint existence of certain observables and hills for certain properties. And this is like an analog of the joint distribution. And then this joint distribution of these observables, some of which commute and some do not commute, is actually what the kind of unifying thing is between different experiments and between different sample spaces. Now the question is that whether this particular type of joining or coupling sample spaces that's used in quantum physics, whether it can be captured without loss of information by Kolmogorov's language. That I don't know for a fact right now, but I know that you can construct something more general within Kolmogorov language, so that you can embed whatever is done in quantum physics into that. So that's.
And so I really don't understand quantum physics, so I can't answer that. I can answer a few things about Hilda space and some of this. The way I look at it is, what I'm trying to do is sort of like what's done in mathematics with differential geometry. We can do put differential geometry inside a Euclidean geometry and work out everything in this larger type of structure. And in practice, I think for what I'm doing, everything will be done in a larger Kolmogorov probability space. The question is that the right way to do it? Just like in differential geometry or even in topology, you look at the intrinsic geometry or the intrinsic topology and what you're looking at, not in terms of Euclidean space. And the reason why you want to do that is, well, we understand Euclidean space, that gives us easy ideas. But if you want insight into what's going on and insight into understanding or predicting or looking for good theorems, then you do the, I think Ron would agree, you do the intrinsic sort of structure. It gives you the right group structure, it gives you a whole bunch of right intuitions to work on. So I also deal with incomplete information. I try, when I'm going to try to do the, complete the quantum thing. The way it works is, you run an experiment or something and you get probabilities. For some things, I have a counterfactual logic where I can ask lots of questions. Most of these questions I can ask, I don't have probabilities for. So I look at the questions for which I have probabilities, he might call them observables, and I look at that. And in my system, the way I define propositions, everything through a little trick, they form an ortho lattice, or ortho-complemented lattice. So I'm already half there to what I want. Plus, now they're probability functions, so they're orthomodular lattice. So observability is giving me the lattice, and that's where I start with. The general theory about what observables are gives me a lattice. Then I start adding things. And what I'm adding is I'm staying away from quantum probability as far as possible. I agree with quantum probability, we need observables as a basis to start with to get incomplete information. That's the natural sort of thing. And then I add things that make sense in psychological experiments and using it cross psychological experiments, and hopefully get something interesting out of that. And so I'm in the same ballpark that he is in. He has much more mathematical development than I have at this time.
Brian?
Okay, so here's a question. There are various phenomena that both of these approaches want to explain. And I'm interested in how much overlap there is. So the quantum probability is supposed to explain order effects. And I rather think that your intuitionistic probability isn't aiming as
It can't explain order effects, but the quantum part can.
Yeah.
This other one can.
So are there, what's the overlap, and what are the parts that are different about the phenomena that the two of you are trying to explain?
Well, I have two things I'm trying to explain. One is what I can do with the intuitionistic like logic or topological event space. That's one type of project. That works very well for the Kahneman-Tversky heuristics that I said represented and availability. It explains the type of phenomena that the people publish in the literature. And Jerry would say that's the low-hanging fruit to take.
Well, we did that too.
Yeah, they did that too, and they did more. They ran additional experiments to bring out the richness or the contrast, mainly between the two, which I have not done. So there's that part. Then there's a part like I'm trying to do, I think, including like Edibar is. Plain intuition. If I look at observables, then if I take the conjunction of two observables, it's not observable. In the Platonic world, in my Platonic world, I can take the conjunction, but I don't know what probability it is. I don't have information for pinning down the probability. So I don't consider it, right? There might be more subtle methods where you actually can bound the probability between the upper and lower limit and use that information. I don't do that. That would be the standard, that would bring it back to standard probability theory, is to use that extra information. But that information isn't all that good. It makes things enormously complicated in my system. So I take something very simple because I'm applying it to psychology. Psychologists think simply. We've seen ample evidence of that. They just look at simple cases and they can't even agree on the basic simple cases of only 4 numbers. But the subjects also are even simpler. So I want to use this idea about bounded rationality, so I want to keep the computation simple and just basically look at what I could do with observables. And so it may not be from a Bayesian point of view, I'm throwing out information, which I think is sometimes a good thing to do.
I think one thing that we do, I think the way to characterize the quantum work is not just order effects. It's more trying to make predictions for sequences of measurements across time. So that's what I was presenting earlier yesterday. Order effects, just measuring 2 things at 2 different times, is just one example. But we've been doing other work looking at how you get a sequence of effects across time and how you do different kind of measurements across time, how we can predict those different sequences across time. So it's more dynamic, it provides a more dynamic prediction power than either what Eddie was talking about or what Lewis was talking about. Now, Jeff doesn't like our dynamics, but anyway, that's our goal, is to develop better dynamics to predict sequences across time.
Okay, so that's a big difference because Lewis has no dynamics.
I'm going to ask some other questions here, but I see some of the graduate students are having to go. So let me just say one thing for the graduate students, because I really love this conference with respect to graduate students. You tend to think that by reading the papers in your class, that everything was just done in this way right here. Right there, there's a paper, and that's all it's done. No, folks, it's not like what you heard today, with debates and with discussions about, no, that isn't what it is, this is what it is, back and forth. So as far as the graduate students are concerned, I think this has been, and well, for all of us are concerned, but definitely the graduate students, because you don't see this. This has been a very, very valuable experience for you. So don't go back thinking, wow, that was fun, look at all the debate. Look at it, this is a model for how you should develop your own theories and things that you're putting forth. Steris.
Yeah, before this conference and after this conference, I didn't know any of the mathematics of quantum physics or anything like that. But looking at it from the perspective, I looked at everything from the perspective of an applied theorist in social scientist, applied sort of theorist of social science, and I'm interested in issues like public opinion or issues of court cases and prosecution and defense, including I have applied models for that as well. And what the idea of taking a different point of view depending on the situation, or having a view of reality that is not the correct view of reality, is something that comes out of it, that I'm getting out of what you have done. The question that I have is that everything seems to be a black box. You need to articulate a mechanism of how precisely these subjects, how they go about to be convincing, more convincing to the rest of us, of how these subjects change this frame of mind, have a story, maybe, and how this, what Jeff's sort of argument about the oscillation and those things, why does this happen? These are sort of issues that I think are important to work on and try to teach to the rest of us and sort of learn yourselves about it and try to how do you change it? Do you need quantum mechanics for that? This mathematics, can you change can you have a different way of moving from the different bases to different sort of state spaces of probability, essentially? Something like that, that your probability, classical probability is defined and you have sort of a mechanism of how you move from one to another. So that's what I would like to learn more about, the mechanism and the intuition for it.
We have this Hamiltonian. We do have a story for it, but we haven't gone into those details and talks because they're too short.
Yeah, the story. What I would like to hear is in Joyce's case, where the two different cases, that the Gore versus Clinton on the one hand, when you have, how did you call it, assimilation, and the other, the contrast in the case of Newt Gingrich and Dole. How did this happen? It's a black box. I mean, I don't know why you get so very different order effects in those two cases.
Right, so actually in the paper, actually I didn't put in the talk, that's a great question. So actually we thought this, actually explains, at least present as attitude, like, of people's mind states, whatever. I feel it's more intuitive actually, according to what I think. So in the paper actually it's very easy to derive what's the relation of the subspace and the initial state. What's the relation between those subspace and initial belief states can result in contrast or assimilation effects and so on. So why that happens? So according to this model at this time, just like the different relation between how they perceive this 2E value the two items that they're evaluating. So it's much like, maybe much like something we have been establishing in psychology, like multi-dimensional scaling model. So everybody has different map of the mind about what things should be, the word should be. So in our case, we of course, subject we can look at that state. So for example, some new data actually about the evaluation on the president and evaluation about the country, we do look at how the subspace, what's the angle between the subspace among different ideologies. So we haven't done enough work into the details yet, but indeed they vary. For example,
The ideologies of the candidates or the ideologies of the voters or those with the subjects?
Oh, the ideology? Oh, so
The ideology of the
subject.
candidate,
the subject,
of the points of
subject,
the
the
subjects.
participant. Yeah, so we do have some like they're meaningful. They're very meaningful. So actually, one thing we argue in the paper is that actually the cosine theta between the cosine theta is the angle between the two subspaces of two subjects is very similar to the correlation. It's very similar to correlation. How you think the two subjects are similar or not. And then that angle together with where you are in your initial state when you will be asked that question is can predict the different types of order effects that are identified in the literature, which is not a key point in our paper actually, because in our model we can produce many different types of order effects, but we just want to link to the original literature people care about. And that's a great question, but I think that's very similar to multidimensional scaling type of idea. Do you want something to add?
I think what happens is the actual time is about 5:28 or 5:27, and I know a bus is coming pretty soon and anything like this. I want to thank the speakers and the audience and the speakers for one hell of a good 2 days. Very informative.